welcome again to OsmoDevCall, the 2021 Christmas Retronetworking Special Edition. So today we will actually not be talking about something that's related to mobile communications, but it's related to communications in general and more specific to old wireline telephony systems before they became IP-based. So we are talking about digital switching of telephony networks in roughly the late 80s to 2000 kind of time frame. Yeah, so this talk is retronetworking at its best. Digital telephony switching covers my research into HCV5. I didn't know much about it at any point in time where it was actually developed and or deployed. So I'll introduce the V5 interface, the protocol stack, the state machines, what this all is all about, how it's useful, and what I have in mind to do with it in 2021, and a bit about my ongoing efforts to do a free and open source implementation of the related specifications. So a couple of acronyms and definitions. You cannot do without them in telecom. It's not just 3GPP, but even wire telecom. So those are not V5 specific, but they're general language that's used in this talk. There is TE is the terminal equipment, meaning your phone or modem or fax or whatever you attach to the telephone line. NT is a network termination. In Germany, we had the NTBR, as the termination for base rate ISDN interfaces that were very popular in the 90s. ISDN is the Integrated Services Digital Network, basically the digital telephone network where not only the exchanges, the telephone switches are digitized, but even the subscriber line is digital. PSTN is the general term for public switch telephony network. So basically anything from whatever the late 19th century to today. BRA is found in the specs quite often as a basic rate ISDN access line, which is a line that consists of two 64 kilobit B channels, meaning bearer channels for voice, fax, or data transmission. A circuit switch data, of course, and PRIA is a primary rate ISDN access line, which is an E1-based interface with 30 user channels, 30 64K B channels. And E1 is a primary line rate interface at 2048 kilobits per second. Which is used a lot in this context. And I guess everyone here knows about E1 and probably also knows about the ICE1 USB, the open source hardware USB to E1 interface that Silver released in the last couple of years, and that was developed in the same community, basically. Well, it was developed by Silver, but well, within the wider Osmocom context that triggered him to do so. So if we look a bit at the history of telephone exchanges, many people are aware that originally telephone exchanges were manually switched. So the nice boards full of phone checks where you plug in the different lines and you manually connect subscriber A to subscriber B. That's basically how telephony first came about in switch telephony in 1878. Around 1900, electromechanically switched telephony was deployed. That's the famous Strauger switches, and in German, the Hebdrehwelle. Later on, we had other electromechanical relay-based switching technologies. Around 1965, the first electronic switching systems that had still analog multiplexer, analog switching matrices deployed came about, and about 1976, digital switching started, meaning that you have digital control, sort of deciding about the switching, and also digital signals that are being switched. So that's PCM signals, pulse code modulated digital voice channels that are being switched in these systems. And basically that's sort of where it starts to get interesting from my personal point of view, and also what this talk will be covering. and the evolution towards this interface called V5. In PSTN networks, since about 1970s, we had the problem that more and more telephone subscribers, of course, are added to the telephone systems. I mean, that it has been a general trend ever since the invention of telephony, the growth of the subscriber base. At the same time, the capacity of the switches themselves increases a lot as the technology proceeds. So with electromechanical switching, of course, there were some physical size limitations on the number of lines you could switch in the switching network, in the matrix, and so on. As that became first analog electronics and then later digital electronics, of course, the amount of size required in the exchange per line got reduced, and also the capacity of those digital systems in general increased. So we have switches that have higher capacity. The operational cost of each of those operating an exchange is rather substantial. So there was a trend towards centralization of exchanges, which means fewer exchanges and more subscribers per exchange. And that then creates the problem that you have this incredible amount of subscriber line wiring going to this local exchange. And the response by the manufacturers of this was to become modular, to have a modular architecture where sort of you first have some kind of later became known as the access network or the access multiplexer. So you have some device that terminates the actual subscriber local loop, which is the wire that terminates the subscriber. And you first go into some kind of multiplexer, and then you go into the actual exchange. And those multiplexers could also be remote, so they don't have to be physically at the same location as the large telephone exchange. So this means you reduce the amount of physical cabling that has to go into a single geographical location. It also helps to reduce the subscriber loop length. As these access multiplexers move closer to the subscriber, it means they have a shorter loop length, and you had a better analog signal quality on analog subscriber lines, and also in terms of ISDN, there's of course a maximum length of the subscriber loop as in how far you can go between the termination on the operator side and the home of the subscriber where the line ends in the NT. This is the subscriber loop length is a problem that we still know today from the various evolution steps of DSL technology. Basically, this was where it started, that the subscriber loop length was reduced to increase the transmission quality, and that is a story that continues until today, where the DSLAM is moving closer and closer to the subscriber to make the subscriber loop shorter. The kind of lengths we are talking about here are still in the kilometer range, whereas today with the modern high-speed DSL, VDSL, we are talking about hundreds of meters of subscriber loop lengths. So there's an order of magnitude of difference in there. So vendors first came up with their respective proprietary access multiplexers. So you had to have the access multiplexer from the same manufacturer as the manufacturer of the telephone exchange. And then there was an ETSI standardization attempt. ETSI is the European Telecommunications Standardization Institute, to standardize a V5 interface, which is a vendor-independent, standardized interface and protocol stack between the access multiplexer and the actual exchange. So if you look at this in a graphical representation, this is taken straight out of the ITU specification. We look at the specs. So they are specified. I think ETSI started with this project, and later also ITU adopted those. So we have both ITU and ETSI specifications. So we have the actual telephone at the subscriber. We have the subscriber loop, basically the telephone line. And then we have the AN, the access network. This is what I said, the access multiplexer, and in the V5 specification that is called the access network, which handles, in this case of an analog subscriber line, handles the analog digital analog conversion, the front end handling, generation of ring voltages, detection of pulses in case of pulse dialing on the analog line, also deals with generating these high-frequency pulses for metering towards the subscriber, and other things related to the analog interface. And then we have some kind of layer 3 protocol entity in the access network. And then we have this V5 interface between the access network here on the left-hand side and the local exchange, which is the telephone exchange on the right-hand side. Where here in this diagram, it's a V5.1 interface. There's two different versions or dialects of V5. .1 and .2. We will look at the different differences between those two as the talk progresses. So we have many of those lines, analog subscriber lines or even ISDN subscriber lines on the left-hand side, terminating in the access network, which then aggregates them somehow and then has this V5 interface, which is E1 based. And therefore, it's part of the PDH architecture. We had a talk about PDH and SDH in case you want to hear more about that as a background. So this is aggregated into an E1 interface, and the E1 interface then is connected to the local exchange. And of course, you can have many of these access networks with equally many E1 lines going in between the local exchange and the access network. But since every E1 line carries 30 B channels, you have a quite high multiplex rate between the number of subscribers you can terminate in the access network versus the lower number of actual physical lines you need towards the local exchange. And since E1 is part of the PDH system, this doesn't actually need to be a dedicated line, but you could also transport that over an PDH or SDH transport network, like a metropolitan area network or something that might exist, interconnecting those two. So it doesn't have to be physical dedicated E1 lines going between those two network elements here. If we look at the V1 architecture in a more more sophisticated representation than the one that we just looked at, this is another diagram from the specs. We see here again we have the access network, and it terminates different subscribers. For example, a classic PSTN analog subscriber or an ISDN basic access subscriber via their network termination going here into the access network. Or another ISDN that doesn't have a network, where the network termination is in the telephone exchange. That's not something that was deployed in Germany, but at least the specs always indicate as an option. So the NT can be more on the subscriber side, or the NT can be in here, which of course makes it rather short here if it's just the ST interface here. But also, of course, analog and digital leased lines that existed in classic telephony networks equally can go into this access network. And then we have here some kind of processing that we will look into more detail. And we have two connections towards the back. On the one hand side, there's a possibility to connect to a permanent leased line service network, which is not very exciting from the protocol point of view, because there is nothing really happening. It's a static configuration. But here on this interface, that's the V5 interface going to the local exchange. And this is the interface that I'm interested in. Maybe a little bit of preview on why or what is of interest to me. Personally, I want to make use of these access network multiplexers and implement the local exchange side in open source software. So basically, I want to use existing decommissioned access multiplexer network with this V5 interface, and then have an open source implementation on the local exchange side, so that one can implement a real, in quotes, digital telephone access network without having all this bulky room-filling local exchange equipment, but just a small access network devices installed. So there's some additional acronyms related to V5. The previous acronyms are general PSTN or ISDN acronyms. The AN is the access network, the LE is the local exchange, the FE is a functional element that's sort of kind of primitive in the protocol between two finite state machines on the AN and the LE side. We have line termination, line circuit, and exchange termination as other acronyms that you see in the drawings, but the important ones are really AN, LE, and FE for the remainder of this presentation. So the kind of specifications, in case anyone wants to look up the references, there is the V5.1 interface that's specified in ITU TG964 and these ETSI specifications below. And there's also the Q3 interface. Actually, I ignored that here on the slides. On this one particularly, we have the Q here at the bottom. That's the management interface by which these systems are commissioned and monitored and managed. And that is a separate interface called the Q3 interface. And there's two variants of it. There's the one for AN, the access network, and there's another one on the local exchange side. So we have another Q interface here on the local exchange as well. I'll briefly have a look at that, but yeah, we'll see at that later. Let's focus on the V5 interface. So if we look at the protocol architecture, we have a couple of different protocols involved here. Actually, yeah. I don't have a protocol stack drawing here. Well, we can look at this small part of the diagram here. So we have the lab V5DL, that's the data link layer. And the data link layer then goes through a mapping function to an enveloping function, the EF, which then finally goes to a physical layer on a 64 kilobit time slot. So we have an E1 line with different time slots, but at least one of those time slots, the 64 kilobit time slot, is used for signaling. And in there we use LabV5, that is a derivative of the LabD protocol, which is the ISDN layer 2 protocol that is used in ISDN access, but also is used, for example, in the ABIS interface on GSM networks and in many other telecom domains. So LabV5 is just like LabD. And we have this data link layer. And on top of that, we have the PSTN protocol and the control protocol. We will look at the functions of those two layer 3 protocols briefly later. Let me first describe a bit what's happening here. So I think these two is still relatively easy to understand. We have two layer 3 protocols on a shared data link layer, but then we have this mapping function and envelope function and those kind of bits. And that relates to the fact how ISDN user signaling is carried over the V5 interface. So if we look at ISDN, let me just see if I have a better slide for this. Do I have a... Okay, we look at this later. Sorry. It's a bit confusing where to start and how to properly... it's convoluted, and no matter where we start, there's always something we are missing at this point. So let's ignore that part for the moment, but just say we have these two protocols on top of a data link layer, and then there's some additional mapping function that we will discuss later. And the same we have, of course, on the local exchange side. Equally, we have the same layer 3 protocols. We have the same layer 2 protocol, LabV5, and the same underlying mapping function and the enveloping function, the EF here. The data link layer, as I said, it's like a LabD. So if you've ever dealt with Q921 or EDSS1 or whatever ISDN signaling or SS7 to some extent, well, not so much, has a different layer too, but at least in ABIS in GSM or E1 lines in wired telecom, you will know what LabD is. But just a quick overview or introduction. So we have a physical layer at the bottom. We have a data link layer connection here. We have well, one end on the left-hand side is the access network. On the right-hand side, we have the local exchange. And the data link layer, that instances that we have here, the point-to-point data link procedures, and this service access point towards the higher layers, now they make sure that there is a guaranteed delivery of messages. So in case a message is lost or is not acknowledged, then it will be retransmitted, and a kind of window of unacknowledged messages. So it's a bit like TCP, you could say, from the IP world, but with the difference that we are not talking about streams here, but about datagrams. So The LabV5 is a reliable and also optionally unreliable. So you both have acknowledged and non-acknowledged messages, so-called iframes and uiframes that carry data, and it provides these services to the upper protocol layers on the interface. So on top of this LabV5, which is basically LabD renamed with some very minor modifications and clarifications, we have two protocols. The control protocol is one of them. The control protocol has two parts. One is common control, the other one is per port control. So common control relates to anything that affects the entire access multiplexer access network, whereas per port control relates to one specific user port, one specific subscriber line. And what kind of tasks do we have in the common control? We have the provisioning or reprovisioning of the system, or switching over to different variants of configurations, for example, also restarting of the equipment. So like global bring up and provisioning related stuff. And on the per port control, we have the blocking and unblocking procedures, which are basically to bring a line into service or to take a line out of service. So let's say a subscriber cancels his subscription, then you would, of course, block that line. Or equally, if a subscriber comes into service, you unblock the line and thereby allow it to be used in the system at all. We also have activation and deactivation for ISDN only. So an analog port would only have blocking and unblocking, but an ISDN port also has activation and deactivation, and that is just because ISDN needs this. So there is a way how in an ISDN basic rate access line, you can put the NT and also the terminal equipment, meaning the phone, into a low power mode, and then there is some activation procedure to bring it out of that low power mode once some service is required from the network. And that's the activation and deactivation procedure. So in PSTN, we have basically the following messages. We have unblock and unblock ACK, and we have block and block ACK for those two procedures. And there's a couple of so-called functional elements that are used. And as I said, these functional elements are sort of primitives that are included in those messages and sent back and forth between the finite state machine. So the specifications always work the way that they specify a finite state machine for a given part of the functionality in the access network and a finite state machine in the local exchange. And then there's these messages going across the V5 interface, how those two talk to each other. In ISDN, we have the same, plus some additional procedures and messages. For example, the D channel can be unblocked and blocked separately from the entire port. And then we have these access activation and deactivation, as I mentioned, an ISDN-specific procedure. And also we can have some performance reporting of the ISDN line. I didn't look at this in detail, but it's apparently about the line performance, probably bit error rates or something like that can be investigated with that. Now, if we look at the PSTN subscriber, we basically really have those two protocols only. The control protocol handles this blocking, unblocking, and the PSTN protocol handles the analog signaling. And that's the part that I want to look at now. Analog signaling in this case means, if you remove the typo from there, it's mostly on-hook, off-hook signaling. So if the subscriber takes their phone off-hook, then that must somehow generate an event that the access network detects that due to the impedance change on the subscriber loop. And it creates some kind of layer 3 protocol signaling message to the local exchange to notify the local exchange that the line has just gone on hook. And then the local exchange must put the audio samples into the B channel for playing a dial tone, for example. And then equally, we have signaling of the pulse dialing that the subscriber is performing, assuming they are using pulse dialing. These pulses are again detected here in the analog front end and are converted into signaling messages that go over the V5 interface and specifically the PSTN protocol inside the V5 interface. And the entity in the local exchange then needs to aggregate those digits and do routing of calls and so on, all the signaling of the telephone call, basically. The PSTN protocol now manages the analog line states, as I meant, on hook, off hook, but there's many more details, and I will give you an example of that shortly. It also controls the timing and duration of analog signal, also the voltage and frequency of metering pulses. Many details about the analog subscriber interface are highly country specific, so every country has their own dialect of analog telephony. And since the V5 equipment was produced to be universal, and specifically the V5 interface is designed to be universal and international, you can basically express all the local details in this protocol. So you can, as I said, specify which frequency and which voltage to use when sending a metering pulse, for example, or what is the amount of current you should use when ringing, or you can configure additional attenuation, I think, of lines and things like that. So yeah, we have one finite state machine for each port on the access network and the local exchange side. In the PSTN protocol, we have already one finite state machine for each port on both sides for the control protocol. So that makes it 2 per port already. And the kind of messages we see here is establish and establish acknowledgement. That's basically meaning that the line has gone off hook. We have signal and signal ACK, meaning that pulse tiling is detected and communicated. Disconnect equally is, of course, going on hook again. And status inquiry, well, of course, the name implies what it is, and you can configure some protocol parameters. And the way how this looks like in a mobile, you see, I'm always talking about mobile telephony. No, it's, of course, not a mobile originated call. It's an originating call, nothing mobile about it. So the subscriber basically takes the phone off hook, which means it's called a seizure event. And here we see the access network in this line. We see the local exchange here, and we see the national higher layer protocol implementation on top. And these LE1 and AN1 and so on are state names. So the specs basically say, well, on the access network, you have these states AN1 to AN5. And in the local exchange, you have states LE1 to LE5, and we have these messages between them, and then the state transitions and the state machines, that's all defined in the specs. So the telephone receiver is lifted off the hook, the line is seized, and that creates an establish V5 PSTN protocol message to the local exchange, which would send an establish indication to the higher layer entity, meaning the actual telephone signaling software. It acknowledges that creates an establish ACK to the access network, and then we have digits that are being dialed, so-called signals, by the phone, which gets transmitted into signal and signal ACK messages here, which gets forwarded to the higher layer protocol, and at some point maybe we want to disconnect the line, and then that is signaled equally here with the disconnect. So we have primitives here locally in the exchange. We have the V5 messages on the V5 interface between AN and LE, and this is events on the local subscriber side. The terminating call looks rather similar. So we first have an established request from the higher layers to the local exchange. The local exchange then sends an established message to the access network. The access network acknowledges that. That gets acknowledged to the higher layers. Then we have signals. In this case, of course, it's not digits that are being dialed, but ringing signals. And at some point, well, of course, the voice call, if the call is established, and then at some point it's disconnected again, and we go back to the initial state AN1 and LE1 in both finite state machines. And that's really all there is to the PSTN ports in V5 access network. So with those few messages on the control side and the PSTN protocol side, we should already be able to terminate analog subscribers into an access network over the V5 protocol. Now, just to give you an idea about the many different states of signals that you can have on an analog line, this is just something to scroll through here. So it's not just on hook or off hook, but you can have normal and reverse polarity, and you can have some battery connected to one wire, or you can have the A wire connected to earth, or all kinds of things, or disconnect the battery, or creating pilot frequencies and changing low impedance and whatnot. So there's a lot of difference. This is only the steady states signals on the analog line. There's another such table for like short signals, like a ringtone or something like that. Not sure, like an intermittent signal that you can also generate on the analog line. For ISDN subscribers, of course, it's slightly more complex because in ISDN we have more protocols and more signaling. So if we look at this model again for the ISDN subscriber, here on the right-hand side, we have the local exchange again. We have the V5 interface between local exchange and access network. In the access network, we have a number of management entities, management over here, and procedures towards the actual, well, here's T, but it's actually the U interface in this case. The ISDN basic rate access. Of course, if we compare it with analog telephony, we don't have this PSTN signaling with analog line states and with dials, digits that are dialed or pulses in analog frequencies for metering. But basically, we only have the underlying physical layer that can get activated or deactivated or blocked and unblocked. And then all the actual call control signaling is ISDN signaling in Q931, Q921. That's the normal ISDN protocol stack. So the way how this is handled in the V5 is that the actual Q921, Q931 signaling, the layer 3, layer 2 signaling of ISDN arrives at the access network and is then enveloped, encapsulated, and tunneled through the V5 interface and then passed to layer 2 entities and, of course, layer 3 entities in the local exchange. Maybe it's a slightly more, well, looking at different graphs, there is this one that we had before. So basically, we have here on the ISDN access side, we have Q921 messages on 16 kilobit D channels. And those messages arrive here on 16 kilobit D channel from the subscriber at the access network. They come into this frame relay function, go into a mapping function, go into an envelope function, and leave on the 64 kilobit signaling channel. And then they arrive here on the right-hand side in the local exchange, where they go again through a mapping function, and they end up here in the Q921 layer 2 and then Q931 layer 3 stacks further up the stack. So basically the same 64 kilobit signaling slot that is used for the control and the PSTN protocol is also used to encapsulate the 16 kilobit D channel from the subscribers. They get mapped and enveloped and transported over the same signaling slot, and then they get basically demultiplexed here into a layer 2 entities in the local exchange. So it's, I think, a rather nice architecture where the access network doesn't have to have any understanding about the protocols that you communicate. So you can have any dialect of ISDN, any version. You can do any software updates that only affect the local exchange. And your access network just tunnels those messages between the subscriber ports on 16K slots and the V5 interface on 64 kilobit slots. So I think it's a rather elegant solution, not having to implement any ISDN-specific stuff inside the access network. So the frame relay protocol, together with the control protocol, is what we need for ISDN subscribers. And this frame relay is really just, it's by the way, it's not to be confused with the wide area network frame relay technology that I think also I've mentioned in some of the earlier OsmoDev calls before. It's just called the same way because it's both some frames that get relayed from left to right. So that's just a tunnel or envelope or encapsulation layer. So if we look at this frame relay in a bit more detail, what happens is that we have lab D frames coming from this arriving. So this is all implemented inside the access network here. On the left-hand side, we again have subscriber ports. So let's say there is a layer 2 message from the subscriber. And then we strip the flag octet at the start that starts the HDLC flag octet that starts the message. We take sort of the header and the information field. We copy that and we generate a new frame, a so-called labv5ef frame of the envelope function, which contains basically the entire header and everything that the user sent, except the checksum, the frame check sequence that is stripped, and the flag octets. So all the payload of the message, including the headers, gets copied, and we add another header on top. It's like IP encapsulation, if you want to think in that way. And then we add a new frame check sequence and flag octets, and we transmit it over the V5 interface towards the local exchange. And the same happens, of course, in both directions. So that's really all there is to it. How does the control protocol look like in terms of ISDN activation? I'm sorry, this is a bit small, but it's hard to show otherwise. So in the end, we have the layer 2, layer 3 instance in the local exchange, which generates an activate request to the control protocol instance for this port in the local exchange, which sends an FE101 signal to the access network or the functional element, which then starts the activation procedure on the subscriber line towards the NT in the terminal equipment. That gets acknowledged back to layer 2, layer 3, and then we can have LabDM frames that go in both ways through this enveloping function on both sides. They get tunneled through. So yeah, that's basically the way how an ISDN port would get activated and the signaling would look like there. Now in, oops, sorry for that. We don't want bookmarks. Now in v5.2, we have some additional protocols. Why were they introduced? Well, v5.1 is nice and great, but it only covers one E1 line. So basically, one v5 interface is one E1 line, and you have a static mapping of B channels on the E1 side, on the v5 side, to B channels or analog lines on the subscriber side. So there is no concentration in terms of capacity, which is, of course, in any normal telephony network, you always have over-provisioning and concentration. So it's never the case that all of the subscribers can talk at the same time. There's always some blocking at some point. And with v5.2, the v5 was extended that, first of all, it could cover up to 16 E1 lines in one v5 interface. So instead of 30 slots, we basically go to 480 slots, meaning 480 calls that can be managed in one parallel at the same time. And so much higher capacity. It also adds support for primary write access subscribers. That would be, let's say, your corporate PBXs or your ISPs with dial-up remote access servers and so on. So primary rate connections to subscribers are supported in these access multiplexers. And we introduce concentration features, meaning that you can have any number of subscriber loop circuits mapped to a much smaller number of B channels on the v5 interface, and they get dynamically allocated. So you can drastically increase the subscriber count by this over-provisioning concentration features. And last but not least, there's also failover between links. Since now we have multiple E1 lines, of course, you could deploy those in a redundant structure, so that if a subset of those links fail, your interface is still running, maybe with full capacity, maybe with reduced capacity, but at least it's still running, and there is a related failover mechanism. So if we look at the v52 architecture, that's basically the same diagram that we saw earlier in the v51 related slide. But here we have new elements. I marked them in yellow here in the background. So We have the normal PSTN access, the ISDN basic access, but we also have ISDN primary access in 2 different flavors. The first one is the one that I'm familiar with. The second one, I think, is of more theoretic nature, like in the basic access. I mean, we have the NT at the subscriber side, of course, and not at the local exchange. So those 2 get added in this diagram. And if we look at the specification, there's new specs. It's ITU-G 965 instead of 964, and a new ETSI spec that covers the V52. The protocol stack is also basically the same as V51, but we have 3 additional new protocols. So the link control protocol, the protection protocol, and the bearer channel connection protocol, BCC, not to be confused with blind carbon copy in emails. So 3 new protocols. Do I have separate slides on that? Well, yeah, here we can see it again in this diagram. It's again this diagram that we had before, but we have these 3 new blocks: protection, port link control, and the protection and the BCC protocol and the link control protocol. So these 3 new yellow blocks on both sides, which are additional layer 3 protocols on top of the same LabV5 layer 2, and everything else stays the same. So the BCC protocol is now what manages the dynamic allocation of B channels between the V5 interface side and the subscriber side. There's basically only 2 important procedures: allocation plus allocation complete and allocation reject, that basically creates such a mapping of a B channel from the subscriber side to a B channel on the V5 side. Deallocation is the inverse. And then we just have some fault and error and auditing capabilities, but they don't add like new functionality to it. The link control protocol that we have in V52 is to identify the different links. Of course, we have up to 16 links in a V5 interface. Somehow those links need to be identified to make sure which link is which on both sides. And blocking and unblocking of such links in case of maintenance procedures and so on. The protection protocol is what handles the failover between the different E1 links on the V52 interface. It monitors all kinds of things like flag octets, meaning if there's some messages at all in the signaling channel, and whether data link layer 2, the LabV5 is established or not. And based on this monitoring, it decides whether a given link is active, and then there's a concept of logical channels versus physical channels, and it maps the logical channels on different physical channels depending on which of the underlying E1 lines are available or not. So significantly more complex than what we had in V51, but then also, of course, it adds a lot of protection to the overall interface. So if we look at the management, this is the only slide about the management. It's quite amazing that they have used the entire ISO-OSI protocol stack for the management interface of these devices. I'm sure it must have been that somehow they saw that the ISO-OSI stack doesn't get any use case anywhere else in the world, since everybody went for TCP/IP and the internet. So they had to try to find a use case where they can put all the ISO-OSI stacks that they had developed. So we have this incredibly complex protocol stack just for managing these entities, these access network and local exchange devices. This is, by the way, only the upper layer protocol profile. It's not the lower layer. There's another spec for the lower layers. But in the end, what this means is we have an OSI lower layer of collectionless network services according to Q811, which in the end uses Ethernet as a transport. So we have Ethernet somewhere underneath there. And then we have this entire stack of ISO-OSI protocols to manage then the managed elements in this device. I didn't really look at it in detail. I mean, maybe at some point when I'm retired, I might find time to look into this. But I think for now, the more realistic approach is to focus on the V5 side, implementing that and just using the management tools of the vendors to configure the devices because it's just a lot of complexity. Now let's look at some real-world implementations of such access networks that support V5. One of those is the Nokia Exos family of products. The one device that I've looked at specifically is the Nokia Exos N20, which supports, it's a 17-slot rack. We will have some pictures shortly in next slides. So you have a sub-rack with 17 slots, and in that you can manage 512 bearer channels. And the slots need to be populated with units. The main units that you can plug in there is the node control unit, which is like the central processor. And then you have PSTN units, basically line cards for 32 PSTN lines or 16 ISDN lines. And then there's another one for 4 E1 lines if you want to have E1 access or more V5 E1 lines. And then the node manager software to configure these. This is how this looks like. So it's a 19 or 21 inch mountable module. You have these 17 slots here. It's, I think, 7 or 8 U high. And we see here on the very right-hand side, we have the node control module on this connector at the bottom. I think there's some more slides where I can speak about the connectors. But this is the central processor. Basically here we have 3 line cards with each of those cards has 32 analog subscriber lines, and then we have all the remaining line cards are ISDN basic rate access cards with 16 lines per card. And the last one were some alarm and auxiliary stuff, environmental management alarms in this rack. So that's a fully populated Exos N20. Now, if you look at the actual modules that we see in such a device, as I said, we have the node control unit, which is available in 3 different versions, depending on the whether balanced or unbalanced and impedance of your E1 lines. I think the one that's more deployed or more more commonly found is this one, the 120 ohm balanced version. So we have 4 E1 lines for the V5 interface on this connector here. By the way, it's rotated by 180 degrees, so it's exactly the other way around from the picture the photograph that I just showed. We have sync in and sync out for the E1 synchronization. Then we have Q1 interface for local monitoring and so on. And then we have the Q3 interface on an on an coaxial 10-base-2 Ethernet, and then also optionally at a 10-base-T Ethernet here. All the wiring diagrams I've seen, they always seem to use the coaxial Ethernet, where I'm always really surprised that somebody would want to use this in production, given the old problem of one interruption or one bad connection and your entire network being down. But well, that's question of deployment. These are the PSTN and ISDN modules. It's really just you plug it in, the backplane connector connects to the rack, and then you have the subscriber lanes at the front. There is nothing else to connect or to modify there. Now, there's other vendors and other vendor equipments, of course. One of them is Fujitsu and DTV Allian equipment. So Fujitsu, I think, is the original developer, and DTV is the German reseller of the equipment, but maybe I'm mistaken. At least that's my understanding. There's many more different modules compared to the Nokia Exos. Also quite strange port numbers, so not 16 and 32 like in the Nokia, but we have 12 or 15 or 21 lines, so completely odd number of lines. There must have a reason for that, but it's sort of it stands out. That's one of those Allian racks. We see many more different module types, and also you need a lot of modules that are not handling subscriber lines. So I think the density overall is lower of this equipment. I would also expect, like technologically, to me, it always looks a bit older than the Exos. So yeah, but in general, it's the same idea. We have some like this module here with the red and white is the central processing or control module. Then we have some E1 modules here, different generations of E1 modules, at least this one and that one. And the subscriber lines then here have these sub-D connectors and power supply modules on this side and on that side in the rack. There's also other vendors. There is Keymile Milegate, for example, which is interesting in that it combines the classic POTS ISDN DSL subscriber, the classic POTS and ISDN platform with a DSL, a DSLAM platform. So you can have in the same rack, you can have modules for ISDN access and POTS access, but you can also have DSL modules in the same rack, and then they have built-in splitters, so you can provide combined analog plus DSL or ISDN plus DSL lines from this type of equipment. Definitely much more recent than both of the two earlier equipments. I don't have a picture of this. And another example is the Siemens FastLink devices, where I also listed the common modules that are related to V5 use cases in this. I find the Siemens the most difficult to understand and most convoluted system based on those informations that I have. Yeah, but I guess that's just matters on what you're used to and how it is being explained to you. So what is my, I always hit the wrong button here. What is my plan? The evil V5 master plan? Well, collect some of these decommissioned access multiplexers. I've been intending to get my hands on those for many years, and I finally found a source of an operator where I can get some. I still don't have them here, but it's almost there now. And the idea is then to create a working setup out of them, similar to what I did with PBXs for the Osmocom Retronetworking setup at the last CCC Congress that happened, like the last physical on-site Congress, and deploy that at future hacker events to allow people that are interested in retronetworking to get analog and ISDN subscriber lines, but also to, of course, be able to show such equipment and how it works and how it's being deployed to interested people. So what do we need for that? We need access multiplexers, basically almost done. We need the documentation I already have, configuration management software I already have. We need E1 interfaces. Well, old DADI cards, or now the ICE1 USB, of course, is the ideal candidate for that. And then we need the V5 protocol stack for the local exchange side. And there's no open source software that supports V5 apart from Wireshark. So at least we have a Wireshark dissector. I don't think there's any, like, it's an unreachable dissector in Wireshark right now. So unless you manually say you want to dissect something as V5, there is no way how automatically this dissector can get reached. Yeah, I guess that's something to work on to be able to look at protocol traces once I start with testing against actual equipment. So in terms of the V5 implementation, I started an implementation for the local exchange side. It's based around libosmocore and its TLV decoders and finite state machine abstraction. The state is currently work in progress. It's only about 3,000 lines of code at this point. I have the core data structures abstracting the different logical parts of the stack. I have the decoding and encoding of the control protocol, and a couple of finite state machines for common control and port control. I also started with the V52 link control protocol, but of course, first I want to get the V51 working, because that's much simpler before moving on to V52 as a second step. In terms of the lab V5, there is already a fairly flexible and configurable LabD code in libosmocore, which we use for LabD, LabDM, LabSat, and Lab some other, I forgot, but many different other LabD-based protocols that we already implement in Osmocom use the same code base originally by Andreas Eversberg. So that is also being used for the Lab V5 in this code base. But yeah, I don't have actual equipment, so it's always a bit of a chicken and egg situation. But I intend to do a bit more coding, and then hopefully in the next couple of months I will get my V5 access networks to interconnect and then start testing and actually hopefully getting something to work. And combine that at this point. But of course, unless you have the equipment, it's always a bit of a, how can I say, a Trockenübung in German. So will be much more fun once the equipment is there. Now, how to integrate that into a PBX or some kind of larger setup? Because in the end, of course, for ISDN ports, we need the ISDN layer 2 and layer 3. For the P channels, of course, that's relatively easy because if we have a DADI-based interface with ISDN USB or with a Digium card, the B channels can just be directly opened by whatever soft switch one wants to use, whether it's Yate or Asterisk or free switch or whatever else. But for the D channels, we have this frame relay deconcentration that we need to do. And in the end, it will have to look something like this. So we have the various subscribers. We have 2 ISDN-based subscribers here, and we have 2 analog subscribers in this diagram to symbolize it. They are connected via their subscriber loop line to the access network. The access network connects with the E1, which carries the V5 interface that goes into some DADI-capable device, whether a Digium card or ISDN USB. And then that exposes the different time slots like normal these do with file descriptors per time slot. And the time slot 15 for signaling handles the V5 protocol. We go into the V5 daemon. That's what I'm writing right now. And that daemon handles all the control. And in addition, also passes the LabDM or demultiplexes the LabDM of those individual subscribers. And somehow needs to interface that then into the PBX code. I'm not sure yet what I'm going to integrate with. I think it's most likely Yate or FreeSwitch or both. And as I said, they can just open the B channels like in a normal ISDN world, but for the D channels for the signaling, we have to create some specific interface. And for the analog lines, equally, we need some kind of non-standard interface, how the PBX can control those analog line states and so on of the analog subscribers on that side. But I mean, first I need to get this beast running and get all the communication over the V5 interface up and running. And once that is the case, then I can think more detailed about this integration over there. But it's the rough plan is clear. The details are to be defined once the work on that will start. And that brings us to the end of this presentation. It was, I think, a bit of a tour de force, a lot of different topics, but I hope it was of interest to some of you. And I'm very happy to take any questions. Did anyone knew about V5 before this talk?
Well, I didn't, certainly. The thing is, you had said that you waited to get your hands on this kind of devices for quite some time. Shouldn't they have been decommissioned now in tons?
In theory, yes, but the problem is always how to get to it. And I've just been talking with somebody who shall not be named earlier today, who told me that basically even all the EWSD digital exchanges that are not used for years, they are still physically there in all the exchanges in Germany. Like, yes, they are no longer used, they're decommissioned, but it doesn't mean that they have been physically removed. Unless you need the space for something else, why would you invest effort and money into removing the old equipment?
Yeah, it sounds reasonable, especially as probably the new equipment is so small that you can just leave 90% staying in the same room.
Probably you're going to affect the structural integrity of the building if you remove all these heavy racks of equipment. Yeah, who knows? But yeah, I mean, I think it's still the right time to collect such equipment. Of course, there are many countries around the world where this equipment is still being used in production and will continue to be used. So there's also still a market for those devices where they're not particularly cheap. So if you look at, for example, on eBay, you can find some, I think, of those modules. I don't remember which particular ones. I think it was Keymile, and it's like 300 euros per module or so that they are still being traded for. And if you think of putting together a rack with modules and so on, it's apparently one can still sell that equipment for quite some money. But nevertheless, yes, I think now is still the time to collect such equipment. 10 years from now, it will be too late. And I think it's to sort of speak a bit more about the larger mission that I think of with this entire retronetworking. I mean, yes, of course, it's fun, and I have a personal interest in that. But I also think it's somehow important to keep all of this technology alive in some way, that it can still be shown to later generations. I mean, we have museums full of Edelmetall and Hebdrehwähler and all the electromechanical stuff, but I don't think we have any museums that have digital switching equipment, and even if they do, for sure they don't have it operational, and that's rather sad, because what we are talking about is like, let's say, the second 50 years of the 100 years history of telephony, or maybe at least the last 30 years of 100 years of telephony switching. So it's a very important part of technology, and I also think it's probably the most reliable technology we've ever seen for telephony, both before or after. It will never be as reliable as that equipment, and yeah, I think it should be something that at least should be preserved in some way, and should be still yeah, be able to experience or to explore by people at a time when this is no longer used in production networks.
For a practical standpoint, when you will now have these modules, what are the operational requirements in terms of, do they need whatever additional airflow, or do they need special power supplies, or is it just the normal 48 volts and they're happy?
I think it's more like 55 volts or so that they need, but I think it's a single supply of a DC voltage that's required. In terms of airflow, I don't know yet. I think for a small configuration, you might get away without too much additional cooling, but I will know once I have the equipment. If you look at the manuals, of course, if you mount a 19-inch rack or 21-inch rack full of these sub-racks, of course you need additional ventilation. But if you use one of those and you maybe only have a couple of modules in them, I'm not so sure whether you really need active cooling, and you don't have environment temperatures of 36 degrees. I'm not sure. We will know. But I would expect this to be, especially the more modern. I mean, these access multiplexers are relatively modern. I would hope they don't generate ridiculous amount of heat. But yeah, I'll see. So the normal mode of installation is that you basically have one of these sub-racks, and then you have one U fan unit, and then you have another sub-rack and another one U fan unit, and so on. That's how they build these entire full racks of those sub-racks. So Weave is asking whether we have TTC3 premises to have sinks or generators. I did not go that route. I think it's test-driven development is nice for things that are really needed in production. But for such a pet project, which is really just to run it as sort of an exhibit, or just for the heck of it, in heck or hack, I don't think that is an approach I would normally take. So I would test it against the real thing once I have the real thing, until it works, and then that's it. I wouldn't go with emulating an access network in whether TTC and 3 or some other language that just means writing a lot more code for something where we don't really need to worry about long-term maintenance or regressions or things like that. It's really just a pet project. Okay, no more questions. Then I will stop the recording. Thanks again.